how does intensity of radiation, flux density, power, and area, how they're related? So here I have a source, a screen. You can see a two-dimensional circle there. And what happens if I make the radius smaller? What happens to the intensity that falls on that screen? If I had a detector there, how about if I make that bigger? In 2 dimensions we have a circle, but how about if we have any source that emits in all 3 dimensions? What will be the surface that we need to consider? What will be the area that we need to consider? How can we find the refractive index of a piece of glass, perspex? How can we find the speed of light, electromagnetic waves, in a material? Can you describe an experiment? Look at the setup carefully. Let's switch on the light box. So, ray of light hits the glass block, appears on the other side. What do you need to do so you can construct the path of the ray through the block of glass? Can you see any limitations of this method? How can you improve the accuracy in your calculation? Do you use one set of results? If you only had one set of results, how can you get an accurate value and estimate also the uncertainty in the refractive index? Let's replace the light box, which produces white light, as you can see. Is that a limitation? Look also at the thickness of the beam with a laser. So we'll add a red laser. Any safety considerations when you use a laser? So there we put the laser in. What do you notice when we use the laser? Is this better? This is a red laser. What happens at the face of the block? What do you see there? We definitely have refraction and weak reflection. What can you say about the ray that enters and the ray that leaves our glass block? Can you suggest an improvement to the practical so we get results so the graphical method can be used? Why is the graphical method better? Let's now look at directing a laser beam at the semicircular block. So we have the laser beam coming in, hits the block right in the center, and the laser leaves out, comes out from the other side. How can you use the information shown to calculate the refractive index of this glass? How about the speed of light in this glass? Remember, we're using a red laser. What do you need to make certain of so that the data obtained in this practical, this experiment, are as accurate as they can be? Let's look at the variation of the previous practical. So I have rotated the semicircular block. We again have our red laser beam coming in, hits the semicircular surface. What happens here? Do we have refraction? Why don't we have refraction? Can you explain this in terms of wavefronts? You must be able to do that. So the laser beam continues then, and when it gets to the interface between the glass and air, it refracts, as you can see. Remember, you must always add the normal line before you can draw the refracted line, ray, or the reflected one. What will happen if we start increasing, changing the angle of incidence? What will happen to the angle of refraction? Remember, the angle of incidence is inside the glass. So we're talking about this point there. So we're going from a high refractive index to a low refractive index. Let's have a look. So we're increasing the angles gradually. Now, to make the experiment accurate, we must always make sure that we're hitting bang in the center. We may have to just look at what happens now. There is the refracted ray, and it's gone. So there is a very special angle, the critical angle of incidence, at which the angle of refraction is exactly 90, and if the angle of incidence is bigger than this, then we have what we call total internal reflection. But for this to happen, we must be going from a high refractive index to a low refractive index. So as you can see there is definitely no refracted ray. Let's have a look at shining laser light into water. So there we go, from air into water. And if we select a very special angle, we seem to end up with the following. What do you see? We don't see refraction at the water to air interface. We see total internal reflection. What are the conditions for total internal reflection? There we go, beautiful. So I'm just following it through. There we go. What can you tell about the angle of incidence for total internal reflection to take place? It must be bigger than the critical angle. How do we define critical angle? What can you say about the speed of the green light inside the water? Let's have a look at, again, laser light passing through our water tank, but now I have introduced a diffraction grating just before the laser light hits the water tank. You can clearly see the diffracted beams, and we end up, as we well know, with a diffraction pattern. Look carefully at the angles made by the first order. So the zero order is the brightest one in the middle. You can see above and below the first order. Assume we can measure this angle, and yes, we can. We can mark the dots, the spots there. We can use trigonometry and easily work it out. How does this angle compare to the angle I would have had if the water wasn't there? So the water tank wasn't there full of water. So the light was traveling through air. Can we come up with a way of finding, based on these measurements, the speed of green light in water? Can we work out the refractive index of water? So assume we know the wavelength of green light in air, and we measure, work out using trigonometry, the first order angle for the maximum with the water tank in place and without the water tank in place. Let's look at blue light going through a piece of glass. As you can see, what phenomenon is illustrated in this demonstration? How can you find the wavelength, the speed of the blue light in glass? If I change the color to green, let's say, or red, will it have the same wavelength in glass? How about the speed of the corresponding light? How is this used in modern fiber optics? What are the conditions for that to happen? Look carefully there. What are the conditions for the light to undergo what is shown at this point? Let's try and use the green laser. So there we go. Similar path. You can try the green laser through another piece of glass. Let's have a look at this one. Here we go. And we can go in reverse. You can also do it like that. Let's look at white light going through a glass prism. Do we get white light back? No. As you can see, we have a clear spectrum formed. What can you say about the order of the colors? Did we expect that? Why do we get a spectrum of colors? What phenomenon is illustrated? What is the physics behind this? So remember, white light going through the prism, we have a screen, and we can see our spectrum of colors. Concentrate on the red and the blue.